Shall we start? So today's lecture, as I'd announced, is going to be just going over some problems as review. And if any of you have, if there's any of the material from prior lectures you want to go over again, I would be happy to. But otherwise, I have just a bunch of problems, and the way it's going to work is instead of me just solving them, we'll just go through one by one where you kind of solve. And so that's what we do. Um, so before I move on, any questions? Anything on the design assignment, which is due shortly. Okay. So let's dive into it. So one class of problems that I want you to be very comfortable with is be able to handle design where you have to use Karnaugh maps to come up with something which is sum of product, product of sum, using AND gate, OR gate, NAND gate, NOR gate, typically those kind of gates. In the process of aiming for a simple expression and also optimizing for the gate count. So those kind of things. So in this example, it's a Fibonacci number circuit. So you are you have to write the truth table, write the K-map, identify. So you should be very comfortable with what is prime implicant, what essential prime implicant, finding a cover, namely a set of prime implicants which are minimal in some sense, draw the logic diagram. Usually I will give you some specification as to what gates are okay to use or not to use. Let's see. So these problems, if you once you're comfortable with the K-map, are pretty routine. The only time you run into some trickiness is when dealing with sum of products versus product of sum. So in one, so you can approach it multiple ways, either De Morgan's or consider the Karnaugh map for the inverted function. So focus on zeros. Otherwise, you approach it in a very similar manner. They're kind of all very similar. The thing to note is many of you been using Logisim as a little bit too much of a crutch. So be sure that you can handle this. The other thing is, I think almost every problem I've offered where there was don't care, some students or the other would ask, can we use don't care? The whole idea of don't care is yes. And at the midterm, if you were to ask questions like that, we will not respond, okay? Because the idea is we expect you to be able to identify when to use don't care or not. So our answer to that would be you have to figure out. Again, so don't care if the specification is silent on what the output should be for certain input values, then they are don't care, and you can map them to anything. Now, of course, in real life, occasionally what may happen is that it was an oversight and one should have given something. So, of course, you will probably go back to your customer or whatever, figure it out. So now in this problem, there is no don't care because every 4-bit combination is a valid number. So there is no possibility of a don't care here. But for example, in the design assignment, which is the second problem, the BCD one, the 4-bit decimal digits, but obviously decimal digits go from 0 to 9. So 10 through 15, so 10, 10 through 111, they are don't cares. Okay, so exploit them. In K-maps, they help you particularly because they can result in reduced logic. Okay, so first step in something like this, let's fill out the K-map. So perhaps one of the thing, if you are rusty on K-maps or whatever, maybe having a blank K-map somewhere on your cheat sheet might be a useful thing as a reminder so that you don't mess it up. But doing it from scratch is pretty easy. Also, just remember, going from one column to another, you only change one bit at a time, and then you wrap around. And same thing with the rows. Um, One thing in this problem, you have to when faced with something like this, where I left it loose, I did not specify any particular input output, right? One thing, if you notice, is I kind of say let DCBA be the number, with D being the most significant bit and A be the least significant bit. If you don't write that, then I don't know what mapping you are using. In the first problem set, I think there were several students who just, firstly, in that case, the inputs were given, but they were not called ABCD. And the students drew the Karnaugh map with ABCD, and nowhere was it specified how ABCD mapped to the 4 bits of input. So if you don't do that, then of course we are at liberty of taking any mapping, and we'll take the incorrect one, and you will get 0 score. So you have to make sure that you specify how to interpret the inputs, the things in terms of which you're going to K-map. If you are given the input names, like let's say I call them, I don't know, XYZ, WXYZ, then you should use WXYZ and not ABCD. So let's fill this thing out. So how would we fill it? So Fibonacci, I've given you where all it's going to be 1. So no one wants to take a shot? How about you? Hello. Okay. The review is going to be you guys working. So yeah, you just tell me what goes in different things. Yeah, fill out the schema. So tell me. So from top left, tell me what should I put. So you 0 0 0 0.
No, I mean like in the box that corresponds to all of those bits.
So 0 here,
One.
then 1.
Wait, the first
Hmm? First one is a 1. Okay, so just speak out. First column, what do I put here? 1? What? 0. Okay, so this one is easy, right? I mean, it's 8 and 13 are going to the other ones. Okay, so, okay, now, how many prime implicants are there?
4.
Huh?
4.
4. Is that what you said? 4. Okay. Anyone else?
3.
3, 4, 3. Anyone else? Okay. So which are the 3?
The top row.
Top row.
The 2 in the 0, 1 column.
The 2 in the 0, 1 column.
And then the bottom one, the top one.
Okay. Now there are actually 4. So what's the 4th one?
1 and 5.
1 and 5. Yeah, exactly. So that's also an implicant. Okay. So implicant is something where I have coalesced things and I cannot go any higher. Okay. So there are 4 out here. How many essential are there? 3. Okay. Which one is not essential? The 1 5 one, right? So essentially, this is essential. This is essential. This is essential. This is essential. The 1 5 is not essential because all the squares it's covering are covered by something else already. Okay, so it's not the sole one covering that. Okay, so we have our essential ones. Then find a cover. So remember, the strategy is essential, as the name implies, have to be there. So you should first include all of them and then see if something is left uncovered. Now, in this particular case, by the time I'm done with all the essentials, I have my cover. Okay, so we are done with that. Okay, generally speaking, that may not be the case. Also, in this example, there were no don't care, so we didn't really have any flexibility of doing it. How many implicants are there? Yeah. 15, yeah. Okay, can you explain for everyone how did you get 15? It's correct.
You can divide the top row into pairs.
Okay.
You get 3 of them, and you can also
You
count each one individually.
you actually get 4 of them pairs, right?
Right.
So it's like for the, and then every minterm is also an implicant. Okay. So you add all of them up, you'll come up with 15. So implicants mean any singleton, pair, whatever, quad, 8. Okay, so you count all of them. Now, of course, we tend not to care about the smaller ones because they are subsumed by the bigger ones, and the bigger ones need fewer gates. So that's why we like bigger implicants. So prime implicants are what we favor. So we normally don't bother about the normal implicants. Okay. Okay, next one. Essentially the same problem, 4-bit Fibonacci circuit, except that now I've given you input is called A3:0. Use a 8-to-1 binary select multiplexer. So binary select multiplexer is one where the select inputs are coded, so instead of being one hot, and you may use additional inverters and NAND gates, and your goal is to minimize the number of additional gates. So we have a multiplexer, it's 1 to 8, so I'm going to draw them like that, 0, 1 through 7. Okay, I have a select input to which I can feed, since it's 3 to 8, so I can feed 3 of the inputs, and then 1 is going to control something else. So I can approach this problem well, I have to pick 3 out of 4, so 4 choose 3 different ways I can select. So there's 4 different ways, depending upon which one I decide to use as part of the data. So let's say for the sake of argument, I'm going to use A2:0 out here, and then these things are going to be dependent upon A3. But that's one of the 4 possible choices I can make. Now what? How would you approach it? Make a truth table, right? So let's start with the truth table. So we decided that we are going to use A3 to control the data. So the truth table would be in terms of A2:0. So I'm going to put that A2:0. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. Except now I'm going to think of my output in terms of 2 cases, A3 being 1 or A3 being 0. Okay, because I want to make the input a function of A3. Okay, so A3 is like an input into this thing. So A3 is false and A3 is true, 2 cases. Now my Fibonacci numbers were 0, so that would be A3 is 0 and everything 0, so that 1, 2, 3, 5, 8, which would be this guy. What else? 13. So this guy, right? And everything else is not a Fibonacci number, so we can put a 0 out there. And now the trick is that when A2 colon 0 is 0, 0, 0, then whatever we present at this input is going to come out at the output. And looking at this row, you see that it is 1 in both cases. So we put a, so this is always true, so this is 1. Then we look at the line 0, 0, 1. And this one is when A3 is 0, it's 1. When A3 is 1, it is 0. So this is not A3. So I'll have then line number 2 is the same thing, not A3. Line number 3, 0, 1, 1, same story. Next one is always 0, so this becomes 0. Next one is 1, this becomes 1. Next one is again 0 and a 0. Did I miss anything? Okay, I don't know if I messed up, but let me go to the official solution. Yeah, okay. It's just drawn the other way. So the trick in these things is to kind of figure out that make maximal use of the multiplexer. So if multiplexer is has 3 control inputs, then that many inputs feed into the control inputs of the mux, and the remaining ones are the ones which are going to control the data line, and then one by one you figure out the logic. And generally speaking, they have to, the choice may matter. In this case, it's probably as simple as it gets. It's mux plus an inverter, so you won't be able to simplify it further. But generally speaking, that may be a choice you have to make. So multiplexer-based designs you have to be comfortable with. How can we make a multiplexer? So so this one is using a 8 to 3 multiplexer. We studied several ways of designing multiplexers. One, of course, is I take multiplexer, push it through a K-map type equation and come up with it. But there are a couple of other ways that we looked at. One was using tri-state buffers or buffers where we have an enable signal. And another one we looked at is to make it using from smaller multiplexers, making bigger multiplexers. So let's say I want to make a 3 to 8 multiplexer using a bunch of smaller multiplexers. Let's say a bunch of 2 to 1 multiplexers. How would you do it? So let's say I gave you an infinite supply of 2 to 1 multiplexers, and I basically ask you to create a 3 to 8 mux for me. How would you do that? Any thoughts? So 8 to 1 mux from 2 to 1 muxes.
Is this binary selector?
What? Yeah, it's binary select mux. Whichever way. If you want to do it with regular one. Yeah. You want to take a shot? Yeah.
I'm not too certain about this, but could you, so you would take all the outputs for the input that you need and put them into one of the muxes, and then feed in the outputs of the 2 to 1s into one of the, each next input for the mux.
Okay.
And then you're pretty much good to go. Oh yeah, and say the select. Yeah, then the select would be whichever's. Yeah, I don't know. Did you define how we select? Is it like a binary
Take your
select?
pick. Let's try both ways. Whichever one works easier for you.
Yeah. Let me just. I don't know. You however the select needs to be, but I guess I got.
Okay. So intuitively, mux says select one out of several. So now you'll have to, if you can only select one out of fewer, then you have to think in terms of groups. So since I've given you 2 to 1, so I'm first going to select from each group of 2, I'm going to select one. So first stage is going to be and then from this group I'm going to select the next one. Okay, so that's the intuition part, right? I mean, so that pretty much we have to do 3 stages. Then let's label these. So let's call these 0, 1, 2, 3, 4, 5, 6, 7. So the first stage is selecting within a pair even versus odd. So this clearly corresponds to the lowest bit in our selection logic. So these guys will all be tied to control select 0, and then this guy will be tied to select 1, and this guy is going to be select 2. So select 2 is selecting which group, group of 4, then and so on and so forth. So you can make multiplexers using buffers. So that's the other way we discussed in the lectures. So if you recall, buffers are nothing but they take their input, push it to the output, except there is some sort of an enable signal. And if enable is high, then so if E equal to 1, then Z is D, else Z is equal to high impedance or X. We are using several notation. Okay, so it's floating. So when we look at these kind of buffers, the main thing to remember is when we are we can tie the outputs together. This is the only type of gate where we can tie the output of one or more than one gate together, as long as you obey certain rules. And pretty much the main rule is the following, that it should never be the case that 2 or more gates have their output tied together and they're driving the output in different directions. One of them to 0, the other to 1. That is not for sure. And the second thing is output should have some value. It should not float, because it is going to feed to some following circuitry, and floating things are bad. So output should have a value, 0 or 1. It cannot float. And it should never be the case that I have conflicting gates. Okay, as long as we follow these 2 things, then you can create all sorts of stuff. So in case of muxes, the basic idea then becomes, I take a whole bunch of these. In our example, we have 8 of these, and then I arrange for their enables to be controlled appropriately, such that only one of them is active and exactly one of them is active, right? So, and this is where we feed our different data inputs, so D0 through D7. And these enable lines, you can conceptually imagine these enable lines, they are coming out of some sort of a logic which is taking our 3 bits of input. Okay, and I have 7 enable lines. What module would you use there? Decoder, right? It's just a usual decoder, 328 decoder. So a decoder plus a bunch of tri-state buffers is another way of making a box. And I described in the class of how this is the strategy to use if you need large multiplexers. Okay? So the decoder, since the output is one hot coded, it will make sure that only one tri-state buffer is on and exactly one tri-state buffer is on. Okay? So that's a digression. So this is a circuit. Okay, let's look at making bigger decoders out of smaller decoders. We had a preset problem, the latest preset on that, where you had to design a 7 to 128 decoder out of a bunch of 3 to 8 and 2 to 4s. In this problem, we have to design a 5 to 32 out of 2 to 4, 3 to 8, AND gates, inverters, blah, blah, blah. And again, let's imagine that you would like to use decoders, so not just make this thing out of AND gate. So can you suggest some strategy that using these decoders, I can easily make using 2 to, so let's start with, if I were to say use only 2 to 4 decoders, what would your strategy be?
Use two to four decoders and then just one AND gate at the last bit.
Mm-hmm. Yeah. So I'll use 2 to 4. That takes care of 4 bits. I'll have 1 bit remaining. I will use an inverter there to create 2 versions of it. And then I have 4 choices from one decoder, 4 choices from another, and 2 from this other, right? So 4 times 4 times 2, that would be 32 possibilities. So 32 AND gates of 3 inputs each. Okay, suggest some other strategy. This time around using 3 to 8 also.
You have 1 3 to 8 and
1 2 to 4, right? So 4 times 8, 32. This time around, I will need only 2 input AND gates, right? And each time I will select one line from one decoder, another line from the other decoder. Okay. So these are it's pretty straightforward to do once you kind of understand that all I have to do is to look at groups of bits and decode them. Okay? And then essentially we are saying that I have every possibility to account for, one from decoder number 1, one from decoder number 2. So every possible combination I have to make use of. So okay. Design a circuit that accepts a bunch of single bits and adds them up. Okay. And we had a preset problem like this, so hopefully it's there. But oftentimes we are in the situation where we have to add up a bunch of, essentially I have a bunch of signals and I want to count how many ones are there, or equivalently how many zeros are there, or other type of questions like, is the number of ones even? Is the number of ones odd? These kind of things that, okay. So if I'm counting things, then essentially I have a bunch of 1-bit numbers and I'm adding them up. That's the way to think about it. And when you add 2 1-bit number, you may get a 2-bit number. And therefore, you will have a bit at 0th position and a bit at 1st position. So you start doing that. So this is what the solution might look like. I start with a full adder. A full adder is something which adds 3 1-bit numbers. And since 3 1-bit numbers when added together may have a value up to 3, therefore I need 2 bits, so it does produce 2 bits of output. It produces a sum output which has a weight of 2 to the power 0, and it produces a carry out which has a weight of 2 to the power 1. And the thing to remember is, as I add, I can only add bits which have identical weights. I cannot add a bit which is in the 0th location with a bit whose weight corresponds to 2 to the power 1, for example. So I take 3 bits out here, produce 2 bits. I take the other 3, I produce this. So again, I have 2 to the power 1 and 2 to the power 0. And G, which is left over, has a weight of 2 to the power 0. Then I take the 3 2 to the power 0 bits, use another full adder. This is going to produce 2 to the power 0 and 2 to the power 1. And I already had 3 bits of weight 2 to the power 1. I add them up, so I'll get bits with these weights. So 3 bits of output, which makes sense because I had 7 input bits, so my count can be anywhere from 0 through 7, which requires 3 bits to be there. So straightforward to pull this thing off. Yeah.
For this one, you have to invert the inputs? For this one, you have to invert the inputs?
Oh, did I mess up? Number of inputs at a logic 0. Yeah, you're right. Yeah. So I guess what I have solved is number of inputs at a logic 1. You have to invert them. Okay. We saw adders in the class, right? Which are made using full adders chained together. They were adders which were designed to add 2 arbitrary numbers. Let's say I ask you, create me something which takes an arbitrary n-bit number but adds 1 to it, or some other constant. Okay, but let's sake of argument. So I have instead of variable plus variable addition, I want to take an n-bit input and add 1 to it, increment it, right? In programming languages, some think of x plus plus. Okay, so I just want to increment it. How would you go on doing it? Now, of course, one solution is take your adder and then make one input to be 0, 0, 0, 0, 0, 1. I don't want to do that because that's tremendously wasteful, right? Because the upper bits were all 0, lower bit is 1, they have known values, so I want to create something more optimized. So how would you do that? Using primitives that we have seen. So basically, I'm taking an n-bit number, let's call it d. I want to produce an output x, and I want to make x is equal to d plus 1. That's what I'm looking for. And if it overflows, then
The carrying input is always 1 bit, right? The carrying of the adder
okay.
is always like 1 bit, right?
Okay, yeah.
So maybe we can use that to that 1.
Yeah, but that's what I was arguing against, right? I mean, if I use a full adder, then it has another input which will have to tie together to 0, right? So I want to avoid that inefficiency. So I don't want to use a regular adder which adds 2 n-bit numbers. I mean, while it certainly can do this, it's an overkill. So I want you to think in terms of, can I simplify it, okay? So can you use something else? You're kind of on the right track.
Like, maybe we don't need to use 2 so we will get two
No,
bits.
no, 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 no. You cannot feed 2 bits of the same number to the same full adder because then you'll be adding them. But have you seen a module which instead of adding 3 bits adds 2 bits? Huh? Half adder, right? So you cascade half adders, and that will do the trick, right? So I take bunch of half adders, except I wire them this way, right? And this is where I feed my D0 through Dn minus 1. Okay, so I just gang half adders together, and that will do the trick. Okay. Think about what implications might be there if my number was 2's complement. I'll let you figure that out. Okay, right now it was sine. What might happen if it was 2's complement? What might happen if I were to say decrement by 1? Those kind of questions. So just think about, but thing that I wanted to emphasize out here is that a regular adder was designed to add 2 variables. But oftentimes we are interested in a variable plus a constant, and in which case you can optimize things. Okay. Yeah.
If we add itself to itself, then we get like shifts.
If you add itself to itself, you get a multiply by 2. Yeah.
Then we can shift it back, right? You just
But
wire.
that's superfluous then.
And like, so we can add the input to itself and with
a 1,
yeah, with the constant 1,
that will give you 2x plus 1.
and then we shift it back.
Then you'll get back x. Right? Because if you shift it back, then that 1 will drop out. So that won't work. Okay? By the way, since you brought this thing up, just wanted to mention that those of the second problem in the design assignment, you are multiplying by 10, right? That's BCD digits. So if I have 2 digits, and the overall value is 10 times the 10th digit plus the lower digits, right? Same story holds true there. Instead of multiplying 2 variables, I'm multiplying a variable by a constant. And therefore you can optimize, and therefore you don't need a multiplier. Moreover, when you are multiplying by 2, for example, then instead of doing x plus x and needing an adder, you just have to shift the number by 1 bit to the left, and which we saw in the last lecture is just wiring. There is no gate needed for it. Multiply by 4 is shift by 2 to the left. Again, that is just wiring. So while in the design assignments we are not checking for efficiency, so you will get your right score. In an exam kind of setting, you will not get any points if you are using unnecessarily inefficient designs. Okay, so just remember. Now let's say I say multiply x by 9. So you can say 9x is equal to 8x plus x. So therefore 8x I can obtain by shifting, and then I need 1 adder. So any number, I can break it up into a bunch of multiply by powers of 2 and then add them together. So just something to bear in mind. And because shifting left is multiply, shifting right is division. So divide by 2, divide by 4, those things work reasonably nicely.
So how come it will be like more efficient since you're using a shifter plus an adder to make the same?
Shifter is just wiring.
An adder is a adder.
Yeah, we still are using an adder, but you couldn't have done 9x any other way. Think about it. You cannot do 9x with a single adder. Right?
So adding is less costly than multiplying?
Oh, way less costly. Recall the multiplier, it had n square adders and n square full adders. Right? It had whole bunch of rows of adders. So multiplying is cost of multiplication grows quadratically with number of bits. Cost of addition grows linearly. Okay. Actually, those, if any of you are in computer science and your algorithm class and all, you might encounter there are actually ways of doing multiplication which go as n log n as opposed to n square, but they're very hard to realize on hardware. Okay, but you could consider it. But still, even then, multiplication is more possible. Okay? You have a question?
If you have a multiplexer that takes n bits of input in each pin, do you just use n multiplexers to implement that?
Which takes each data line as n bits?
Yeah.
Yeah. So kind of depends. Logisim shows it as a multiplexer and each input is a bus. Sometimes you would see following symbolism. Let's say I have a 2-to-1 multiplexer which is 4-bit. Then you might see it drawn like this. It may have a cluster of 4 here and a cluster of 4 here. Okay, and so depends. Look, again, as long as the intent is clear and you label things, that's fine.
Like in terms of implementing it.
Huh?
In terms of implementing it, you just use like n multiplexers.
Oh, yeah, okay. In terms of implementing, you just use n multiplexers and just selects a type together. Okay. Recall arbiter. I bet most of you have forgotten because I never asked any questions on it during the homework. What did the arbiter do? It selected a winner, right? And the way it worked was, arbiter took n bits of input, a request, and then had an n bit of grant. And the idea was that we will, at any point in time, we are going to look at the R inputs, the n bits of R, R0 through Rn minus 1. You start from 0th, and the very first I at which R of I is high is the winner. And then we will make the corresponding grant to be high. So it basically says, finds the first 1 bit in R. So Gi is 1 if Ri is 1, and Ri is 0 for every value of j less than I. And the way we had created this thing was that we had created the circuit. We're starting 0 is at the top, so we're going to start from the top, and kind of essentially the circuit was saying that at each stage I'm going to take the request of the ith stage and I'm going to say, has there been a winner yet? No one yet. Okay, that's coming from the previous bits, and then combine the two to then say, am I granting here or am I telling the next guy that has there been a winner or not? Okay, so we created this 1 bit stuff, and then we just replicated it, and we started out with things tied to that no one yet, so it's high. That is, we're saying that before bit 0 there is no winner yet. Okay. Now the problem with this design is that it's not fair, because every time we are doing an arbitration, we are starting from bit number 0. So if, let's say, bit number source number 1 is very greedy, then it will keep winning because we are every round request and will hog the resource. So we want a fair arbiter. So this problem asks you to do the following, that I want to create an arbiter which is fair. And the way we will do the fairness is the following, that we'll introduce, so it's asking for a modified arbiter where there is another n bit input. So we are creating another n bit input, P. And the idea is that P tells us who the winner was the last time. So P is again one hot coded. So if P4 is high, that means last time around the winner was number 4. Okay? If P0 is high, that means last time 0th one was the winner, and so on and so forth. And what I want you to do is the following, that in the current round of arbitration, the order in which I want to check is the following order. If previous round ith was the winner, then I'm going to this time around give my priorities would be I plus 1 will have the first check, then I plus 2, then I plus 3, through n minus 1, then back to 0, and back to I. So you want to give the ith guy the last priority. Okay? How would you implement this? And there are many ways of doing it. I have one in the following slide, which is a trickier approach, but there are many ways of doing it. So think about that. So how would you, using modules that we have again discussed or encountered in lectures, is there a way you can create this?
What's a tri-state inverter? What's a tri-state inverter?
The one which has the enable thing, so that it outputs X. Floating point.
The inverter.
Huh?
The tri-state inverter.
Same thing. It's invert. So it's normally outputs invert of X and otherwise float. You can have tri-state version of anything. Okay. So how would you create this fair arbiter? Think about it. And by the way, don't, when faced with these kind of problems, when you say use any type of basic gates, okay, don't get spooked by it because you can always, if you need a multiplexer or a decoder, you already know how to create those. Okay, so you can always say, hey, I need a 4-to-1 mux. This is how it's built, and now I'm going to use it as a black box. Okay, so you can always do that. So don't worry about that part too much right now. First, think of how will you approach this problem. And we also know our current arbiter, obviously. Okay.
Here's a messy way. Like instead of we have one wire indicating if there's 0 from the first one, we can have like a bunch of wire indicating if there is a 1 from the first the 0th bit and the second bit. And
Now, how would that help? Remember, I'm already giving you an extra set of n bits, right? I mean, so now I have R and a P. Each bit has 2 inputs coming in. Yeah.
You just have n arbiters, and then you could like rearrange the inputs for each one, and then enable the one that corresponds to the one not coding.
Say it again?
You can have n arbiters, or rearrange the n bits. So like for the first one, it would be like 0, 1, 2, 3, and the second one would be 1, 2, 3, 4, so
Okay.
And then you can just use the arbiter which corresponds to the enable.
Okay. You're on that's certainly a valid solution. So you are saying n arbiters, which are trying each possible n rotations of these, and then I'm going to select the one bit. Okay. So you will have this, and potentially a multiplexer is output. So n arbiters and a multiplexer. And of course, I need the rotated versions there. Could you do something else? Okay, so that's valid. Could you do something on the input side and use a single arbiter? So I have an arbiter which always prioritizes from 0 onwards. So
maybe if we choose this one, and next time we will definitely not choose this one. So can we just like kind of turn it on?
rotate it, right? So we have talked about shifters. Can you create a rotator? So something which takes D0 through Dn as the input, takes the Pn as the inputs, as a second set of inputs, and produces a rotated version of D, a version of D which is rotated by I. And that you can create using multiplexer or tri-state buffers and a whole bunch of things. So let's say I had input coming in D0, D1, D2, D3. Let's say P2 was high. That means I want to give priority to P3 first, right? So I would output such that the output order is X3, X0, X1, X2. So I have just rotated and put the output. Okay, so that you can achieve via a bunch of multiplexers or even more cheaply via a bunch of tri-state buffers. So that's another option. Okay, so I can either create a winner based upon every rotation and select, or I can rotate the input and then have a single arbiter. So what I guess the point I'm trying to make out here is that when faced with these kind of problems, see if there is a creative way you can make use of modules that you have already seen and apply them. And again, this would be a problem by problem sort of thing. There's a third approach which is sort of tricky, but it actually works. On first glance, you would say, hey, this is not a valid circuit, but it actually is. So the way it works is the following, okay, out here. So yeah, let's see. So this is from the TA, okay. So first what we do is, the basic idea that we want to create is the following. Remember, in our original circuit, the signal which said no one yet, we started out from 0. And then we just percolated down. What we are now going to do is the following. We are going to create this P sub I as that signal. Remember, one of the P sub I is I. So that's our starting point, right? You're going to move from that point on. Everything else is 0. So what this modified circuit does is that if P sub I is high, Pi is high, then essentially if this is 1, then this is 1. So this becomes our starting point. It basically is as if this input doesn't even matter. It doesn't exist. And then I create the same arbiter except that I connect things back. So let's say if this P2 was high, then it's as if I have cut the arbiter out here, and now I have an arbiter which starts at location 2 and wraps around. So depending upon which P was high, now the reason I said this circuit is weird is because it has a loop. And I've often said that loops are needed for sequential circuits. But that's a very carefully crafted sentence. Loops are needed for sequential circuit, but that doesn't mean all loops are sequential. This is an example where we know that one of the P's is high, and that breaks the loop. So so under the condition that the P inputs, one of them is guaranteed to be a 1, this circuit actually behaves like a combinational circuit. So I'll let you ponder over it. The slides are, I'll put them on Piazza. I think I might already have. But think over it and convince yourself that this circuit will also work. And it's obviously a lot cleaner than the other argument, others, because we're just using a standard, just a slight variation of our standard arbiter. Okay? So sometimes the answer, therefore, may be to modify an existing piece of logic a little bit to coax it to work. So you should be very comfortable with how decoder, multiplexer, arbiter, adders, subtractors, how they are implemented. Okay, because a problem may ask you to, problem may in a sense require you to kind of dive down to that level, not simply use them as a black box. Perhaps that's the kind of stuff you should put on cheat sheet maybe sometimes, because I realize arbiter is one of the trickier circuits we discussed. So make sure that you and add a subtractor, that was another one which is a bit tricky. So just make sure you're comfortable with those. Okay. Any questions? Okay. Now let's move to sequential circuits. So I know a lot of you have had some pain over FSMs in the recent assignment. So let's go over some of the examples again. This is actually, I think I had it in the lecture also, but so design a circuit which has one input W, one output Z. All changes in the circuit occur on positive edge of the clock signal. Essentially, basically saying that the flip-flop is positive edge triggered. Output Z equal to 1 if W was 1 during the 2 immediately preceding clock cycles. Okay. What happened? Okay, I think my pen has run out of battery. Okay, so so in this case, what we have is so we want output z equal to 1 if w was 1 during the immediately preceding 2 clock cycles. So one thing to keep in mind is that since the state only changes at the clock edges, we update the state only at that time, then if I'm making a Moore machine, then that in effect is saying that I'm examining the inputs also only at clock edges, because output is independent of the output only depends upon the state in case of Moore machines. Okay, so but in any case, whereas in the Mealy machine, output goes to the output is affected by the input purely through a combinational set of gates. Some of you from office hours, I gather, were struggling with that concept. So again, in case of Mealy, output is a function of both input and the state. State we know only changes at the clock ticks, but the regular input can change at arbitrary points in time, and therefore output can change at arbitrary points in time. Whereas in Moore machines, output is a function only of the state, and therefore output can only change at that point in time, and the input changes in between clock ticks, therefore have no effect on the output. Okay. In real life, any input to an FSM is going to quite likely come from another circuit operating on the same clock, and that other circuit is going to be changing the output at clock tick boundaries also as a consequence. So in real life, what happens is inputs also change soon after the clock tick. So one FSM will change the output soon after the clock tick, and that output is input to another FSM or another data path, and that examines it at the clock tick. Okay, so everything happens at clock tick generally. But going back out here, the problem basically said that, look, what we want is that the output should be 1 if W was 1 during the immediately preceding 2 clock cycles. So what we see therefore out here is the following. Out here we see that input was 1 at T3, was 1 at T4, and therefore at T5 output is 1. Another way of saying is at a clock tick we saw W to be high, another clock tick I saw W to be high, then I arrange for the output to be high subsequently. So how do we approach something like this? We could say something. So on reset, we start in the start state, A, and Z is 0 because we haven't seen anything. Some of you seemed to struggle with this concept that if input can be, we don't know whether input can be 1 or 0, and therefore I need 2 FSMs. This was the example where I guess I forgot what it was precisely, but I think we were looking for 0 to 1 transitions or something like that there. So no, it's a single state machine. Okay, you have to be prepared for both the eventualities, that the very first input can be 0, very first input can be 1. What the initial state should be would depend upon the problem specification. In this case, it's obvious that since we are saying output should be 1, if the preceding 2 inputs were high, that kind of basically suggests that when we are starting up, output should be 0, okay, because we haven't seen any input. So we start out in state A. We keep spinning there if we see our W equal to 0. The moment we get W equal to 1, then we move out here. So this is the transition that we take place. We'll make when w equal to 1. So meaning of meaning of state B is that we have seen 1 1. Okay, and then if I'm in that state and I get a 0, I go back because that means I will not see a run of 2. But if I see a w equal to 1, then I say go to state C, and state C meaning is preceding. I've seen 1 and 1, and before that it was all zeros. Okay, I've seen at least 2 ones in a row. Okay, since the last 0. So I start outputting 1, and I keep spinning there if I get more 1s, because if I'm getting more 1s, then the condition that the preceding 2 inputs were 1 continues to remain true. And then the moment I get a 0, I go back to A. So we create an FSM like this. My strong suggestion is think as more machines. Okay, some of you tried to argue that something can be implemented as mealy and not as more, and vice versa. Mealy and more, if you are willing to ignore the clock delay part, are perfectly equivalent. There is nothing that you can implement in one and not in the other, and vice versa. So the statement that something cannot be implemented as mealy but can be done as more doesn't make sense. What you can say is something cannot be implemented as an FSM. That's a fair statement, but it's not correct to say that I can. Now, again, with the caveat that if I'm seeking a circuit which is immediately responsive to the input, then of course it would be mealy. But ignoring that little detail, most of these problems are kind of immaterial to that. Anything more can be done in mealy or vice versa. The number of states may change. There might be a clock delay, but they can be done. So I end up with this FSM, and then next thing is you create a state table. So FSM, the state diagram, state table, and the final circuit, they're all equivalent. They're representing the same thing. Okay. So in the state table, I have the states listed. Now, looking at this guy, this is more machine clearly because the output is associated with the state. I basically then say, what is the next state? The next state is a function of W, but output Z is not a function of W, so there's a single column out here. So I write down all the possible things, and at this stage I leave the states in terms of mnemonics ABC. So in the diagram, I had an arrow from A to B when W was 1. So so from A I go to B if W is 1, and here if I was in A, I stayed in A if W was 0. So that's what you see, that from A to A if W is 0. So once you have the state diagram, you create this table, which is still symbolic. If it was mealy, then output will also depend upon W, in which case you can have another column W and then just have a single column for next state and output. There are many different ways of drawing these truth tables. They're all kind of similar, equivalent at some level. Next thing, you assign bit patterns to these things. So in this particular case, we decided I have 3 states, 2 bits are sufficient, so I'm going to use 2 bits. And therefore, I make A to be 0, 0, B to be 0, 1, C to be 1, 0. What about 1, 1? Well, it don't care, because in context of my problem, that state never happens. So for that state, we don't really care what is the next state, and we don't really care what the output is, because that should not occur. Let's say I had done 1 hot coding. Then I would have used 3 bits, and therefore, and only 3 of them are valid states. The other 5 would be don't cares. So how many don't cares you have depends upon total number of possible patterns. So all that happened in going from here to here is that I replaced A by 0, 0, B by 0, 1, C by 1, 0. And now we have our standard truth table type thing. And the thing is, I need a combinational logic which produces 2 bits of next state and output Z. So I need a combinational logic which is producing 3 bits of output, and it is taking as input 3 bits of input, right? One is the real input, W, and 2 bits of current state. So I have a combinational logic like that. Use your K-maps. So this is the K-map for W1. Sorry, let me. So I have the K-map for first bit of state, second bit of state, and also for Z. Excuse me. So I go to the usual K-map type analysis, or if the thing is simple enough, then just by hand directly, and then you create your gate network. Okay. So I could go from English language description back to this, to the circuit. Now, sometimes we may ask you to go the other way around. I may give you a circuit and say, draw the state diagram for it. Now, this is where there's a slight nuance, and we had, I think, the problem 8C was like that. I had given you a circuit and I said, go back. So this is where a nuance enters. Our original problem, the English language version, had only 3 states. 4th state was don't care. But if I'm giving you this circuit, all you know is that it has 2 bits of state, and therefore, as far as the circuit is concerned, because we don't know what the problem description was, then the circuit has 4 states, because all flip-flops can take 0, 1, and therefore 2 flip-flops, 4 states. So if I were to ask you to draw the state diagram of this, then there will be 4 states in it. Now, presumably, 3 of them will look like the way they previously did, but the 4th one would look something interesting. So remember, the 4th state was 1, 1. That is the one we had ignored. If I look at this guy, if Q is 1, if Y2 is 1 and Y1, if the current state is 1 and 1, then what would happen? So if both Y1 and Y2 are 1, then the next value of Y2 would be W, and next value of Y1 would be 0, because Q bar would be 0. So this gate, let me see if so what would happen is, this gate would see a 0 at its output. If this is 1 and this is 1. Whereas this gate would be a 1, so this AND gate would be enabled, so I will see a W out here. So if current state in this circuit, if current state is 1, 1, then depending upon W, I would either end up at 0, 0 or, 0, 0 or 1, 0. Okay. And once I end up in 0, 0 or 1, 0, I will never come out of it. I'll never go back to 1, 1. So when you enter into 1, 1, then you will take one of the 2 branches, and that's it. So the state machine, the state 1, 1 would look like something like the following. There will be 1, 1. It will have 2 arrows going out, one corresponding to W equal to 0, and the other corresponding to W equal to 1. And so the state 1, 1 is kind of a funny one, which is we just leave it one clock tick, never to come back. And that's fine. So we can have these kind of states which I may start out in, but I'll get out of it. Once I get out, I never return. We can also have states where we get trapped. Once we reach them, we never get out of them. Okay, so, and they're perfectly fine. You may also get, as a result of these things, you may also get into, given a hardware, you may encounter state diagrams where there may be disconnected components. Some states may be connected to each other, and there may be some other states which are isolated. And that's fine. All that means is I can never go from state in one partition to a state out here. That possibility doesn't exist. They're all legitimate. But the bigger point I want to make out here is, given a hardware, all 2 to the power n states are possible. Because we don't know who designed this machine for what purpose. Okay, in this case we know, but if I just throw a piece of hardware, you don't know that. So the task of figuring out what this machine does depends who designed it. I don't know what the intent was. You really cannot answer that question. Now, you may see some interesting patterns in it, and I may very well ask you a question like, what does this machine do? Like if you see a machine and all you see is a chain of states going in a circle, you know it's a counter. I mean, that's the human intuition that you would have. So sometimes looking at the machine circuit like this, you may have a reasonable guess what it was meant to do. But at other times, you don't. In this particular case, if I had given you this piece of hardware, might be hard to say it was actually designed to detect a pattern of 1, 1. Okay, maybe there is some other interesting pattern also it detects. It kind of reminds me of, you know, you see often these puzzles where there's some numbers listed and they say, what's the next one? Depends upon what your concept of a pattern is, right? I mean, some people see one pattern, some people see other patterns, some people don't see any pattern at all. Same thing out here. So given a piece of hardware, what it does, yeah, you can draw a state diagram, you can draw a truth table, but going back to the English language description is, generally speaking, not possible. At least not without some other contextual information, like maybe you know that this is a state machine for a traffic light controller, and then maybe you can reason about it, but otherwise not. So you should be comfortable going from English language description to the truth table to the circuit. You should be English language description to state diagram to truth table to circuit, and you should be comfortable going from from circuit to truth table back to state diagram. Going back to the English language description, there is no recipe for it. Questions on this? Yeah.
Yeah. So for this, is the number of flip-flops always going to be equal to like the log base 2 rounded up of the number of states?
No, we can have one-hot coding.
Okay.
We can have even more superfluous coding. Okay, so all we know is it's going to be at least that many.
Yeah.
Okay, but it can be arbitrarily large.
So would you recommend doing one-hot coding for like in the test situation because it's a lot easier?
If unless there are cost constraints given to you or something else, one-hot coding, yeah.
Okay.
It's a lot easier to do.
How are FSMs set to their start state?
Say it again?
How are they set to their start state?
In this particular case, there is a reset signal, so presumably that's what we're going to be using.
But like, what does it do?
Oh, so what will happen is at power of time, there will be a pulse. This is a negative polarity reset. What it means is that at power of time, the set would be held low for a short while, and that will bring the flip-flop to 0, 0. That would be the typical usage pattern. Okay. But there are also times in which flip-flops don't have resets, in which case they start in a random state. And then you need to design the circuit or design your logic such that it will come out of it. Okay. You should also be able to draw timing diagrams, as in what will happen over time, and accept a description in terms of timing diagram which we had earlier. Okay, this is this kind of stuff. Thing to keep in mind, and this is a subtle thing I just wanted to point out. Okay, I have deliberately, I guess I have drawn it that way, but one of the things you see out here, how I've made these W's a little bit after the clock edge. Okay, because the idea is that W is coming from some previous circuitry which is operating on the same clock, and therefore W itself, whenever it's changing, is changing a little bit after the clock tick. But generally speaking, it doesn't have to be that way. If W is coming from some outside world, some physical entity, in which case it can happen at arbitrary point in time. So look carefully at W. Y1 and Y2 are being generated by us because that's a state update, and therefore they will always change a little bit after the clock tick because the state is updated at that time. And likewise, Z is again updated as a result of state change in a Moore machine. So in a Moore machine, Z will also change only after the clock ticks. On the other hand, if it was a Mealy machine, then Z can change whenever W can change. So state diagrams hopefully are obvious. Okay. So this is a slight variant. What we want to do is we want to say, so previously it was if the previous two were 1, 1. Now we want to say that I want to output high if previous was 1, 1 or 0, 0. So I'm looking for two patterns now. Okay, either one of them is fine. Choice. So a state machine now becomes different. So what we do is we start out in reset state. At this stage, we have not seen anything. Okay. Then if I see so the way to look at these kind of problems, at least the way I find most convenient is, first think of all the distinct cases that can take you to the right pattern. So we are looking at two patterns, 0, 0 and 1, 1. So what we do is we draw them out. So one is this 0, 0 situation, and the other is the 1, 1 situation. Okay, so I make those two cases out. So I get a 1, I get a 1, I was lucky, I got a 0, I got a 0. And now start filling in the remaining edges. What happens there? So I got a 0, I go to state B. In state B, one of two possibilities happen. We get a 0, which is a lucky case. If I get a 1, then it's a potential start of a 1, 1. So I will go to the state D. And if I'm in state D, if I get a 0, that means it's a potential start of a 0, 0. So I go to state B because B's meaning was I have seen 1, 0. And then from state E, if I get a 1, I stay put there because I keep getting 1s. So and if I get a 0, I go back out here, and likewise from the state. Notice how state A, I never come back to it. After the first clock tick, I will leave state A one way or the other, and then I'm always out of it. So in this particular case, I have 5 states needed, and therefore I will need at least 3 bits, and then rest of the approach would be very similar. Again, you can do one-hot coding, you can do more compact code to do that. Now, how to go from the English language description to something like this is there's no recipe. Generally speaking, in some problems, by looking at it and with having enough experience, you know it can be done. Coming up with, so there are 2 types of issues you will face, and you need to be prepared for both of them. One is you want to come up with a good FSM. By that I mean not have unnecessary states. Okay. Now it turns out there are systematic ways of optimizing a state diagram. That is, you can find out what states are actually superfluous and eliminate them. I haven't taught them to you, so you don't know them yet. So your only recourse right now is to come up with a good design. Okay, minimal number of states as from a human perspective. The other type of issue that you may face is, and you have to be prepared, I may very well ask you, it may be that an FSM is impossible. Okay. Remember, FSM stands for finite state machine. So a very crucial part is that the problem has to be such that a finite number of states are possible. Okay. So there are problems in which number of states need not be finite. I cannot solve them using FSM. And just bear in mind, I'm not saying that they cannot be done using Moore and what can be done with Mealy or vice versa. No, they cannot be done with FSM, period. Can someone describe to me a problem where I cannot do it in finite number of states? Yeah.
A counter that keeps going, never reset. Well.
That's a ill-posed problem because when you're okay, but you're right. Count number of, I don't know, number of people on the planet. Maybe it will keep growing.
Like
okay, something like that.
Like constant clock.
counts every clock tick. Okay, that's infinite state. But that's so obviously infinite state that not very interesting. So tell me something more interesting.
Summing a converging series.
Huh?
Summing a converging series.
Summing a convergence. Again, because it's the problem definition itself is infinite, so stands to reason that it would be.
So we don't count whether or not there's an equal number of ones and zeros in input?
Equal number of ones and zeros, yeah, because the difference between ones and zeros can grow infinitely. So that's a good example. So what? Okay. Something else? How about palindrome? So I basically ask you, I'm getting ones and zeros, and I'm basically asking, is the string of ones and zeros that I have received thus far, is it palindromic? Everyone knows what palindrome is? Anyone knows it? Okay, so think about it, right? I cannot do it using FSM. So there are plenty of problems where FSM is intrinsically incapable of recognizing those strings. Computer science as a whole sort of theory behind these kind of things, but basically finite state machines can recognize, in terms of computer science, languages which are regular languages, but there are languages which are not regular, which are more powerful, and there are lots of things which fall into that category. There are even languages which no computer can recognize. Okay, that besides, but finite state machines are less powerful than, let's say, a Turing machine, and a whole bunch of other type of computing machines. Finite state machines are intrinsically less powerful. So, faced with a problem, be prepared that an answer could also be that it cannot be done using an FSM. Okay, so you'll have to kind of reason a little bit about it. That does it can it be done or not? So just sort of think about it a little bit. So we saw a few examples where obviously they could not be done. Okay. So here we go through the same sequence of things. I'm going to skip that. Let's look at another example. FSM to divide by 3. So design an FSM that outputs the result of integer division by 3. The input is the dividend in binary. The states represent the current remainder, and the output is the quotient in binary. Okay. The FSM accepts the binary dividend 1 bit at a time, most significant bit first, and generates the binary quotient 1 bit at a time, again most significant bit first. So what's happening out here is that I have a box to which I'm feeding the dividend. Okay, divisor is 3, so I'm feeding, so like x by 3, so I'm feeding x. X has arbitrary number of bits. So what I'm doing is I'm feeding x 1 bit at a time. Okay, most significant bit first. So, okay, so most significant bit, and then the rest of the bits are following. But I haven't told you how many bits it has. Okay, we have an arbitrary number of bits. And what you have to produce is the binary quotient 1 bit at a time. Again, most significant bit first. So for example, if I give you a large number in decimal and I say divide by 3, you can always start from the left, right? I mean, that's how we do the long division. So I can always start outputting the result from the left. The state has to keep track of what the remainder is. Okay, thus far. The number that I have seen thus far, if I had divided that by 3, what the remainder would have been. So, so the thing out here to look at is the following. You have to go back to your arithmetic a little bit here to kind of reason about what might be happening out here. So let's say the value of the number so far was n. Okay, so I've received some bits. Let's say they represented n. Okay, and let's say a new bit came in. Let's say that bit is b. So the new number that I have now, let's call it n prime, then that n prime is 2n plus b, because I previously received n, now I got one more bit. So that number conceptually now is shifted. So it's 2n plus b. So my new number is 2n plus b after I receive a bit b. Agreed? Okay. Now let's think of various cases. Now the previous number n that I had, there were basically three possibilities. It was a multiple of 3, it was 1 modulo 3, or it was 2 modulo 3. Right? All numbers that I had received thus far will fall into one of these three categories. So it was 0 mod 3, 1 mod 3, or 2 mod 3. And now you can reason about each one of those cases. So if it was 0 mod 3, and so it was of the form 3 times some number plus 0, after the digit b is entered, I have a number 6p plus b. Remember, we just said that the new number after b is entered is 2n plus b. And if the previous number was a multiple of 3, then the new number is going to be 6n plus b. And what is 6n plus b modulo 3? It is b. So that means that if b was 0, I'll go to state 0, or stay there basically. And if b was 1, I will go to state 1. Right? Consider the second case. Previous number was 1 modulo 3. So that was of the form 3p plus 1. Now a bit came in, so the new number would be 2 times the previous number plus b. So it would be 6n plus 2 plus b. And now again you can say what is the new number modulo 3? It's going to be 2 plus b. So if b is 0, the new state is going to be 2. If b is 1, the new state is going to be 3 mod 3, that's the state 0. And then finally, if the old number was 3p plus 2, because it was 2 modulo 3, then the new number would be 6p plus 4 plus b. Again, I do the mod 3, I'll get 2 options. So by reasoning about, so what's happening is, since I'm getting bit at a time, the key insight you have to realize out here is that the new number is 2 times the previous number plus 1. And this discussion that I have had, you can literally kind of apply it to any, I'm picking the example of 3, but you can apply it to 5, 7, whatever, any number, right? I mean, the same logic kind of holds true. It's just that the number of states you will have would be 0 through whatever your divider is minus 1. So if I say create something which is spitting out the result divided by 5, then it will work that way. So actually, if you notice out here, we have just created a divider, right? We have created something which actually gives me the divider, and it actually gives me the remainder also. At any point in time, I can stop, say I have given you all the bits. Whatever bits you have sent to me thus far were the result, and the state is the remainder. If I want to now get those bits in parallel, then we can use that shifter that we talked about in the last lecture. So I can always convert this thing into a parallel result if I want. So we just saw how to create a divider, except instead of a combination circuit, it's a state machine, and it takes n clock cycles to divide an n-bit number. So it's a slow divider, but it's a divider nevertheless. Look through this example carefully and convince yourself that it is doing the right thing. I know it is somewhat complicated, but this is the hard step, this reasoning of what you should do. Rest is routine. Again, I have my state machine following that logic, and then you can go through all the other steps. So in the remaining time, we have like 15 minutes, 20 minutes, 18 minutes to be more precise. So let's look at some examples, okay? So I've just left it at high level. So the syntax out here is the following. This says I have inputs which can take 3 values, 0, 1, and 2. Maybe it's a 2-bit input and 2 patterns occur. Every clock tick I either get a 0, 0 or a 0, 1 or a 1, 0. Okay, 1 to 2 parallel things. and I'm asking you the following, that I'm going to send you these symbols, and then I'm going to stop. I'm going to send you some sort of a stop signal. So maybe there's a third input, a stop signal. And what you have to tell me is that the bits you have received until the stop signal, what was a pattern there? So this state machine is saying that that string I received had exactly 2 2s. So remember, my string could, before the stop sign comes, the string could have had getting 0s or 1s or 2s, and then the stop sign comes. At the stop sign, at the stop symbol, you are going to go and sit in a state. But one of 2 states, success, failure. And success is defined as that the string which came from start till the stop sign came had exactly 2 2s. So first question, is it a finite state machine problem? Very obvious. Okay. How would you approach it? What would your state machine look like? At a very high level. We don't have to design it. So what states do you think we will need?
No twos, 1 2, 2 twos, and 1 1 2.
And more than 1 2. So, and that's a failure state. Okay. So I'll start out in no 2s, and I'll keep spinning there as long as I get 0s and 1s. Then the moment a 2 comes, I'll move to the state called I've seen 1 2, and I'll keep sitting there as long as I keep getting 0s or 1s. And the moment I get another 2, I'll move to the state called 2 2s, and I'll keep spinning there. And I'll keep spinning there until a 2 comes, in which case I'll go to the fail state. And from every other state, if it's a stop sign comes, I go to the fail state. Let's look at the next one. So this time around, my inputs are binary, 0 or 1. And what we are looking for is that it has the same number of instances of substring 0 1 and the substring 1 0. So what we are looking for is that the string that I have received, the number of substring 0 1s in it is the same as the number of substring 1 0 in it. Is it FS finite state or not?
It can be represented as an FSM because the number of instances will always be either 0 or 1 way.
Exactly. So that's the main. So this is not like the other problem of difference between 0s and 1s, right, where it could grow unboundedly. Here, every 1 0 has to be followed by a 0 1 before another 1 0 can come. So the difference is in a short band. So it's a finite number of states, and those are what you're going to represent. Okay. So in effect, you're basically saying they are the same. 1 0 is ahead by 1, or 0 1 is ahead by 1. Those are the 3 possibilities, and you're going to jump between them. Okay. So right on there. Let's look at the third one. 0, 1, 2 are the symbols, and ends in 0, ends in 1, 1, or ends in 2, 2, 2. Okay. So we are basically saying just before we stopped the string, okay, then I had a 0, or I had a 1 1 1, oh sorry, 1 1 or 2 2 2. Anyone? Let's take a shot. This part of the room is very quiet. How about you guys? Anyone? Take a stab. These problems I will not provide the solution to. So,
You state for 1, 0, for 1, 1, and for 2 1s, or for 1, 2, 2 2s, and 3 2s.
say it again.
So I think you want to state for 1, 0, for 1, 1, and 2 1s, or for 1, 2, 2 2s, and 3 2s. And imagine that each of those are in a column.
Okay.
If you encounter a 0, just go to the 0 column. If you encounter a 1, just go to the 1 column. If you encounter another 1, continue down the 1s column.
Okay, you're too detailed for me, but seems to be the right track. The high level way I was thinking about it is the following, that if you think of your stop symbol as yet another symbol, then basically I'm looking for 3 patterns, right? I'm looking for the pattern $0, $1, and $2, where dollar is a stop symbol. And then it's my good old pattern matching problem, which you've already seen. Okay, so you can, so again, going from this description at this level, this kind of plain English, to the design, there's no one right answer. Okay, whatever works for you would be okay. I'll not go through the other two, but I'll let you figure it out. The last character of W, which is the string before the stop symbol came, the last character of W appears nowhere else in W, and the size of W was more than 1. That is, there was at least 1 or more, so there was at least 1 character. Okay, so the last character of W appears nowhere else. So we are basically saying type. Let's say, I don't know, XYZ is a valid string. ZXYZ is not valid because Z was the last character. It also appeared earlier. Okay. Any thoughts? And of course, in this case, we have A, B, C, D, E as the 5 possibilities. Is it finite state? It is. Yes. Okay. Take a step.
I was thinking maybe like slowly branch out with all the different combinations.
Too many combinations. So firstly, note that these kind of problems are often very easily solved if I were to allow you to have multiple finite state machines, right? I can have one for each letter, and then it's simple, right? I mean, then it becomes like, have I seen, if I just let you say, focus on the pattern that nothing but E followed by E, followed by dollar, right? I mean, I can do that, and each one of these characters, and then I can take the result of each one of those state FSMs and say only one of them, at least one of them should have succeeded. Okay, so I could do that. But combining out here, I mean, one way to approach this thing is that, look, at some level there are 5 distinct possibilities prior to success. Last character was E, and I only saw 1. I didn't see E, so I'm looking for strings of the font no E followed by E, and the moment I see another E, I fail. Okay. Another condition is similarly with D and with C and B and A, so I kind of create 5 forks and then have a fail condition leading out of them. So essentially, one branch would look like keep spinning. Anytime you get anything other than E, go to a state where you keep spinning as long as you don't get an E. And the moment you get an E, you go to the special state, and you keep spinning there as long as you don't get an E. And the moment you get an E, you fail, and create similar branches for the other 5. Next one contains at least 2 ones with exactly 5 characters between them.
I have a question about the previous answer. If you forked it for every character and then continue forking, wouldn't that have a node for
No, I'm not continuing forking. So I'm basically saying imagine 5 prongs out of the start state. Each prong consists of, the first prong consists of anything but E. The next prong is anything but D, and so on and so forth. And then in those prongs, then I see an E, I jump to a potential successful situation, but exit out of it if I again see the same character. So I can find those stuff. What about this one, the last one? Yeah.
Doesn't, if you say anything but E, anything but A, anything but that, doesn't that imply that you're using the same state multiple times? Because anything but E is also satisfied by B, C, D.
Oh, okay. I know what you're saying. So obviously that doesn't work. Let's see. So how will I do it? Okay. So I will go with this is a good catch. So that doesn't work. Okay. So I say A, B. Okay, so I guess we have to do the other way. Okay, so I have 5 forks corresponding to A, B, C, D, E. And then we look for the recurrence of that character to take us to a failure state. So basically, I'm potentially, once I reach this state, so I take a fork on A, I go to a state where I've seen an A, that's potentially the last character, and then every time I get a character, I kind of jump to, that's potentially the last character, and then validate. Okay, we'll have to think about it, but I'll let you. These are all FSMs, by the way, so you should build a solution. The last one is contains at least 2 ones with exactly 5 characters between them. Okay. So just think about it. There are plenty of problems in the book, but these kind of pattern detection type problems are a favorite in courses like these, usually with some twist sort of thrown in. And so try them out. Just Google, you will find plenty of examples online, but the textbook has several. So, and by the way, there are also certain digital logic textbooks which are available online, so they have problems. So these are very generic problems which are offered in courses like these. Okay, you'll see that certain kinds of problems have become very popular. Pattern matchings like these. You have LED, whatever display drivers. The TS covered some of them. They tend to be very common. Various sort of things related to additions and stuff like that. So just practice, but eventually it's not so much how much you practice, but how you approach the problems. Because the problems conceptually are relying on a very small set of techniques. So the part which usually throws students off is the part of going from English language description to a design strategy. And that, unfortunately, is not something that you can say, okay, I'm going to exhaustively study and come up with a whole bunch of things. Unlikely. So just approach them as if you might approach writing a program, a software class, same kind of thing. They have a bit of a element of, they're kind of like puzzles, maybe. You're looking at it that way. In terms of the core design techniques, there are very few out here. Okay, one is the whole K-map based approach, and the other is this whole FSM pathway. And the third one is the MUX decoder related things. There are just small number of techniques. So just approach these things in a cool, calm mind. You'll do fine. Questions? Just a couple of minutes. Yeah.
By changing FSM from Moore to Mealy, can you sometimes take off one of the statements?
You can. Mealy can eliminate some states, you're right. As I mentioned earlier, try to stick to Moore. I may have Mealy the other way around, which is I may say, here is the circuit as Mealy or Moore, okay, or so that way you may end up. But when you are approaching these problems where you have English language description and something, stick with Moore. Keeps life simple. Particularly when you are going to be designing things in logic and all. Any other questions? Okay, so the TAs will go over some more problems tomorrow. I think some of them we are drawing from last year's midterm. I will not have office hours on Tuesday, but the TAs will. The other thing is, I know there are 2 of you who need special accommodation for the midterm. I don't know if are you okay, don't have to answer whether you're in the class or not, but you need to report to my lab, 1762 Boyter Hall, at 3 p.m. Okay, and Salma, the TA, would be there, and then you will most likely have to stay put in my lab for the entire exam. For rest of you, cheat sheet, 1 8.5 by 11 page, both sides, okay, nothing else, no textbook, no electronic devices, you don't need them. In the exam, very important that you write in the space provided. You can do extra work, we'll give you some pages, but at the end of it, the solution, the answer has to be provided in the space that we get. We are going to be using Gradescope again, and we'll be uploading, you won't be, so you don't have to deal with that pain, but we will not look anywhere else for the answer. It has to be in the space provided in the exam booklet. No blue books, you will have all the pages necessary in the exam booklet. Okay, so see you well on Tuesday during the exam.